So in the email, I sent out a link. Let me just see what that is. That link was here, uh, and I realized I didn't put the date on here, so it's my fault. But I put the link Icebox, the first refrigerators, and asked people to go through it. I'm not gonna read it or anything, but just um, this is like the first refrigerator. They called them ice boxes because they didn't have a compressor and a sealed system like refrigerators. Before that, people, if they killed a chicken, they had to cook and eat it to like the same day or at least the next morning. And just imagine taking chicken and buying it from Publix, and then the next day you leave that chicken on the counter and you want to eat that chicken the next day. I mean, that's what people had to do before they had refrigeration. So this was just a pre-read that I put out, like how that refrigerator was created. I have one or two short videos I want to play and everything else. How you doing, Ricky? Anyways, the first
I'm
refrigerator.
good. Yeah, no. No worries.
So the first refrigerator was basically what they call an ice box. What the guy's looking at is where they actually store the ice. They have a giant block of ice and they throw it inside there, and that's how they kept food cold. But we use those today as coolers. Like, you're gonna go to the beach and your packet, filled with ice. That's what that is. So it didn't freeze, and the ice melted, so it didn't last forever. Now, if you look, they insulated the doors on this. Look how thick the door is. It looks like a small bank
Mm,
vault or a small safe, but
mm.
they insulated it. Yes, Rick, you got a question?
Oh, no, no, go. I'm listening, bro.
All right, no, just your microphone's on, so I'm hearing like noises. So I don't know if you're
Oh,
trying to
I'm
speak.
sorry. I'm mute. I'm muted.
Yeah, you can unmute if you want to talk. So, anyways, um, when people first started getting refrigerators, they used something called an ice box, like in the last picture. And a guy would come on a horse-drawn carriage and bring you a block of ice to your house. And even the milkman, milk was made every day, and they were in small jars, almost like when we have like a Pepsi style jar or whatever. And the people had to use the milk that day because they had no way to keep it cold. So these ice boxes were more like giant coolers, and you see it says drain for melted ice. If you ever see an old movie, a lot of times what they did with that drain is they ran it into a bowl, and that would be for like the cat or the dog to drink water. That's what they did. They collected that water, and the cat or dog drank out of it. I mean, I don't think it was originally designed that way, but people would catch the water and the pets would drink it, so they'd have their own water. So this was the first type of refrigerator before they created something called a sealed system. Now I have a video. This is a comedy one. This is the Three Stooges delivering ice. So check this out. It's about 2 minutes long. 10 blocks of ice. They're like, heck no. They didn't want to go up the stairs with those blocks of ice. So this is actually what happened back in the day. They had people deliver ice like Amazon, and they bring a big block. Obviously, it's
I'll break your head.
so that's how they delivered ice. Let's fast forward just a little bit. So she wanted 10 blocks. Look, by the time they got to the top, it melted.
Hey, Mo! What a brain. To the ice.
So
What a brain.
this is the actual ice box, like what people had in their house. That was their refrigerator. Again, this class is designed to enlighten you on everything that a refrigerator
I
is.
got home all right with this cake.
All right, and enough of that. But I mean, it was difficult back then. But not everybody had electricity. Everybody had kerosene or lanterns, and they cooked with gas, or they cooked with coal or fire, and refrigeration just wasn't a thing. So when they started mass producing food, like cows and chickens, and they had to butcher the animals to try to take them to places like actual butchers that would service it. They did come up with commercial refrigeration, which was like an ammonia-based system.
If you're all in agreement.
And this is an ammonia-based system. I'll play the video in a second. Ammonia-based systems, they still use these today. I worked on a mobile trailer that had a small refrigerator, and it had a flame. It had no compressor. And in the video, you'll see it. This is back in the 1850s, so you're talking about 125 years ago. No, 175 years ago. They had these ammonia-based systems, and what happened is there would be a flame down here at the bottom of the unit, and it would heat the liquid ammonia and cause it to boil and come up. So this was, instead of Freon, it was ammonia. And then it would go into a condenser to condense that ammonia from vapor to liquid. And that's the same thing we do with a compressor. We take high pressure refrigerant and we change it into high pressure liquid in the condenser. So that's what's happening to the ammonia, is that we're liquefying it here. And then it comes down here through something similar through a metering device like a cap tube system. And then this was the actual evaporator that the ammonia absorbed heat like Freon and turned from a liquid to a vapor, and that liquid would come down. Now, some of this refrigerant did not turn to liquid, so that's what you see this blue here, is that blue would be remaining vapor that didn't condense in the condenser, and then it would be all connected back together again here before it went into an absorber that absorbed that. And then down here, like an accumulator, it would accumulate that refrigerant, make it a liquid again, and then we'd heat it and start the cycle all over again.
Was this considered a sealed system, or was
this was the first design of sealed system, and the refrigeration wasn't really designed for food storage. It was how to make ice, and using the ice for like ice boxes and stuff like that. Here, watch this video for a minute. It might answer some of the questions you have.
You'll be contrary. This is the good old method of cooling things. But science says, tut tut, that's much too crude, and presents the modern housewife with the refrigerator. Now, if she wants to keep something cool, she
Now this is an ammonia-based refrigerator.
And that's the burner. Eau de cologne or any similar spirit is a great absorber of heat, and the more heat it absorbs, the quicker it evaporates. When the spirit vanishes, the hand is left quite cold. In the same way, liquid ammonia evaporates into hydrogen. So watch this diagram. In order to vaporize or boil, the ammonia draws all the heat possible from its surroundings. And there, briefly, you have the secret of the refrigerator. When the hydrogen gets saturated with ammonia vapor, the freezing stops, so it becomes necessary to supply fresh ammonia and hydrogen. A steady flow replaces the old inert mixture, and the gas or oil flame causes it to flow through the whole refrigerating system. The flame heats the liquid in the boiler tube, and the combined ammonia and water vapor rises and flows through a number of other tubes, as shown. By way of the vapor cooler and water separator, it eventually reaches the condenser.
So I'm going to correct myself there, that based on what he said, and I've only worked on one or two ammonia systems, is in this condenser, it's separating the refrigerant, the ammonia, from moisture. Did you hear he said water? And so I'm assuming this might be water, and the absorber here is trying to remix that back together again. But notice that we have different colors for different temperatures and pressures. So the neat thing about this was you didn't need electricity. All you had to do was have a flame, and then they used a thermocouple or thermopile, which was like, it's like a thermistor, but instead of changing resistance with heat, a thermocouple will generate a small electrical voltage by heating, and that would hold the gas valve open, and that's how it would like cycle the gas too, with some sort of temperature control. So you could use this to create refrigeration and not have a compressor. And so they have those even in like campers and trailers and Winnebagos, that instead of using a compressor, you could use a propane or natural gas flame, or you could actually use 120 volts or 12 volts with an inverter. You know those things you plug into a car and then you get an electrical outlet. So they would have an electric heating element instead of a flame, and the electric heating element would cause the pressure and cause the ammonia to flow through. The drawback behind this is ammonia is very toxic. So, if you had a refrigerant leak, there is no, oh, let me repair this leak and recharge the system. When I looked at the trailers that I saw, it was funny. They had a company called Haddad's who does commercial food and stuff for like the movies and TVs. So for a while, my company serviced, I think it was one movie Tom Cruise did down here at a bar in Fort Lauderdale. But this one I saw the ammonia was the Charlie's Angels. They were trying to redo the Charlie's Angels about 10 years ago. And in downtown Miami, they had the trailers and they had a giant warehouse that they created like the main office. And the trailers that these people used, none of the refrigerations worked. And when I priced it out, I told the guy, listen, that whole system that you're seeing here in the video gets replaced as a complete assembly, already charged. You just have to unbolt it and bolt it in. You couldn't go there and charge it with ammonia. So that was a drawback, that this system was in these campers, but the whole evaporative system was sealed towards the outside of the trailer. Even though it was recessed, like you had to access it from outside, it was all sealed. So the refrigerated part that the customer got, if this system leaked, it wouldn't leak ammonia into their refrigerator or their home. It would leak outside the trailer or camper. But because of how toxic it is and as corrosive as it is, if it gets on your hands and everything, it really wasn't that good for a home-based system. But if you saw that one video, the lady had this same exact system.
The ammonia is now condensed and flows along to the evaporator. There, together with a supply of pure oxygen gas, it's pumped in. At the same time, the old mixture is pumped out. Up against such fearful odds, the evaporator freezes. The cabinet is insulated with pressed cork. This makes any leakage of heat a very slow process. The latest insulation material is aluminium foil on waxed corrugated cardboard. Ah, that tastes good. Now, what about a nice cool drink served by a nice cool waitress from a nice cool fridge?
All right, so basically that was like the first refrigeration system, and how they produced ice, and in some cases they were in customers' homes, or let's say in a restaurant or something like that. They were really expensive. I think I read somewhere, and this was back in the 50s, a refrigerator was $700. Now, back in the 50s, cars were only $1,000, $2,000. It was like buying a car. It was amazingly expensive. So we go a little bit further.
In this video, we will talk about the history of the refrigerator, about how were people managing to keep their foods cool before its invention, how were the early models work.
So what he was showing you there is, okay, so what did people do before refrigerators? Well, especially if you lived up north, you had the option of wintertime to make things cold. But if you go deep enough underground, it's about 50 degrees all year round. I remember going to Louisville, Kentucky, to Mammoth Cave National Park, and it was like 55 degrees in the caves all year round. It could be 0 degrees outside, the cave's 55. It could be 100 outside, the cave's 55. So people had built these outdoor storage systems. It wasn't as good as a refrigerator because it wasn't as cold as 40 degrees that we need, but it was a refrigeration system. So I'm not going to totally play this video. I'm not going to take forever, but I want to just skim through a couple parts of this. What happened there?
And how the technology providing refrigeration evolved until today. Before the refrigerator was invented, people were using ice houses to provide cool storage for most of the year. Placed near freshwater lakes or packed with snow and ice during the winter, they were once very common. Natural means are still used to cool foods today. On mountainsides, runoff from melting snow is a convenient way to cool drinks, and during the winter, one can keep milk fresh much longer just by keeping it outdoors.
Okay, so let's go on to the next thing because, like I said, I'll provide these links of the videos in the description of the video when I post them on the website. I want to just do a couple of more chapters and then put the videos with the chapters. Okay, so what are the most basic components we need to make a refrigerator? What sealed system wise, what do we need once we've got rid of the ammonia? Now we went to an actual refrigerator with a refrigeration system. What are the most basic components we need, refrigeration wise? Anybody got an idea?
I'm assuming a container, so the box itself, right?
Well, no, the refrigeration system.
So like the seal system, you mean?
Yes.
Right, so you need a compressor,
Okay.
Yeah.
Compressor.
evaporator.
Fan of some sort.
No, that's not the sealed system. We're not even going to electrical components. We're saying, okay, so now we had to create a refrigerant system that wasn't harmful to people, like ammonia. So we had to create refrigerants. So a compressor, evaporator, two other components.
Condenser.
Condenser and
Metering device.
metering device.
Right.
We'll also call it cap tube. Cap tube. Okay, so what you're looking here is a chest freezer or an upright freezer. That's all they have. They have a compressor, evaporator, condenser, metering device, cap tube. Now, yes, there's some electrical controls, and I'll get into the electrical part of it later. But, you know, they don't have no fans. No, they don't have an evaporator fan. They don't have a condenser fan. It's basically a refrigeration system that's controlled by temperature. That's it. It gets cold, it shuts off. Okay? So let's take a look at some of those. Here's an upright refrigerator by freezer by Frigidaire. Now, if you look, the actual shelves in this freezer are the evaporator. Every shelf, look at this, every shelf has refrigerant tubing running through it. You can see it down below here. And if you can see, this is the actual replacement part. It comes with the heat exchanger, the cap tube, and suction line, and you can replace this. And there's a small hole right in this corner. And I don't know if I can zoom in on it. Let me see if I can zoom in on it. There's a small hole right there, and you can see the pipe that runs down through here. And that's this pipe, it's curled up, that you push down and you connect it to the compressor and your dryer filter. So it is replaceable, and this is the evaporator. But every single shelf has Freon flowing through it. Now, just like your chest freezer, I couldn't show you any pictures of that, the condenser and the evaporator are in the walls. The condenser on this unit is in the wall. So we don't need fans. And this would be a freezer. And just like I said, they just put a thermostat right here. That thermostat turns it on and off at temperature, and that's it. We're done. So here is the schematic for it. We have the cold control, which is your thermostat, a compressor, very basic, very simple. We have a door switch and a light. What is this right here?
Is that like a power button?
It says power, but
Power on?
it says power on, but if you could read a different language, I think that's French, allume or enciendo means light.
Ah.
And
Okay.
actually, that's just a light that's outside the fridge that if a customer doesn't go into their freezer every day, and people get a chest freezer because their freezer and their fridge don't hold enough food, but they don't go in there that often. So if the refrigerator cooling stops, they might not find out till a week later that they haven't been in the freezer. So they have a little light on them that you can walk by and see the light on, at least know that there's power on and it is connected. You know, it doesn't mean the compressor's running and cooling, but sometimes they'll put this in the circuit here with the compressor. What would that do if I put it in the circuit with the compressor? If I put it right here, like connect it where C is and go to B.
If the light is blown, it's not gonna kick on the compressor, I'm assuming.
No,
Because it's in series.
but if no parallel. If it's here down
It's
underneath
parallel.
the compressor, it's parallel, but they're both in series with the cold control, your thermostat. So when your thermostat cycles, that light would cycle on and off. That's very similar to like an oven. When the oven comes on and off, there's a little light, usually say heating, and then once it reaches 350 degrees, that light goes off until it turns it back on, and it cycles that back on and off. So they could do these lights in different ways. I just wanted you to realize, okay, that's what this light is. Again, this video or this presentation is going to be one of many, and I'm going to build a whole thing from the ground up what a refrigerator is. So I understand this is very simple, very basic, but it's going to work into every single component, its function, how to test it, what does it do, and how to read the schematic for it as well. So we're starting with small steps and working our way up. This will take some time, but it'll be a complete class like you went to school every day. So if you look here, here is the electrical, a basic refrigerator circuit. So let's identify these components that are in this system. If we look here, basically we have a cold control and a compressor, but we're not seeing in the diagram the components that help the compressor start and run. So if we went a little bit deeper into the schematic here, these are all the components that you would find inside this upright freezer. And I'm just going to draw lines to it. We have the power cord here. So these arrows represent the power cord. This actual pitchfork means that's ground, but that's what we call chassis ground. Chassis ground are all the ground wires on the appliance that have a green wire that's screwed right to the frame of the machine. Now power comes in through here and it goes to the thermostat. That's this piece right here. This thermostat is what's sensing the temperature. It has a capillary tube around it. The capillary tube is usually filled with an oil or a gas that as the refrigerator temperature changes, the pressure on that tube changes and causes this switch to cycle open and closed. So when the compressor shuts off, the box starts to get warm. The thermostat capillary sensing that applies pressure to the switch, it closes and turns the compressor back on until it reaches temperature. And thermostats are not very good at keeping exact temperatures. If you put a refrigerator at 36 degrees, for example, the thermostat is not going to turn off at 36 and turn back on at 36. It keeps an average temperature. So if we, let's just say that we put it to 36 degrees, we set it to 36, and the compressor's running now because we're trying to get temperature. The temperature starts dropping as the compressor's running. We might get as low as 32 degrees or even colder than 32. And at that point, the thermostat shut off. Now, the switch may have shut off a few seconds before that, but the refrigerant system's still flowing and everything else. So there's still some cooling being created even when the compressor shuts off, but very, very slight, time. So at that point, it shuts off. The temperature's going to start to rise again, and it's going to go above 36 degrees. It may come back on at 40 degrees. Okay? And at that point, the thermostat's going to say, hey, it got too warm in here, turn the unit back on. Have you ever been in your house and you're cycling the temperature in your air conditioner and you're like, man, it's warm in here. And then a second later, the AC comes on and then it gets a little cold in here and the AC goes off. So what happens is it keeps an average temperature of the on and off cycles. So they will go above and beyond 36, but the average temperature is going to be about 36 degrees. If you took 40 and 32, that makes 72. And if you divide that by 2, 2 can go into 7 2 times and leave 12. 2 can go to 12. No, 2 can go to 7, what, 3 times, right? My math is bad. 2 times 3 is 6 with a remainder of 12. And then we got 2 can go into 12 6 times. So what does that make? 36 degrees. So that's how we keep temperature. Ovens do it, dryers do it, any appliance that heats or cools, its accuracy at the temperature that the customer requests is not as good on a mechanical thermostat it is on the newer computer controlled ones. So when we get into them, we'll talk about how more efficient they are in the electronic controls and how more accurate the temperatures are. But in this case, that thermostat's going to cycle the compressor on and off, and you can see the compressors here, and we have a relay, and an overload is inside the relay. I didn't put the capacitor, but there's a capacitor that plugs right into this relay right here. And in looking at the parts breakdown of that Frigidaire refrigerator that we just looked at with all the all evap freezer shelves, had a capacitor in it. So that refrigerator would have every single one of these components: compressor, relay overload, and thermostat, a simple refrigeration circuit. And that's all we need for cooling, whether it's a freezer or a refrigerator. It all depends on what the thermostat's going to cycle it on and off at. Now, if you guys got questions, stop me. So what are the pros and cons of the upright freezer with a shelf type evaporator? Are there any pros or cons to that type of system?
I'm assuming it's more consistent freezing temperatures or more consistent temperatures in the upright?
Not necessarily. The upright is making it convenient that, you know, when you have a reach-in chest freezer, stuff tends to get piled on top and you forget what's on the bottom, or you say, I know I bought a roast a while ago, and you have to dig through a bunch of crap to get to it. Where the upright freezer is really, if you look at it, if I turn this thing on its side, if I take this thing and do this, what do I got? A chest freezer.
Yeah, okay.
It's the same thing, and the only difference is I put the evaporator in shelves and not inside the wall. So it does the shelves pro wise. Yeah, it's a convenient of the customer as far as getting food in and out, but it's not any different in temperature. Now here's a con. Well, think of the cold air as water. Okay, so this whole thing is colder inside than it is outside. And if I open this door and this was water and not cold air, have you ever been like, you go from outside into someone's house and you open the door and you feel this rush of cold air hitting you? Well, when you open up the door of an upright, your cold air tends to flow out and warm air comes in, and it empties out pretty quickly. But if we had a chest freezer like we have here, hot air rises, cold air falls. So the cold air would be like water, so when you open it, the cold air remains in the freezer. That's why, like, when you go to a grocery store and you got frozen sliced meat packaged right there, sitting in an open air environment. There's not even a lid on it. But they refrigerate it. It runs longer because it's not insulated at the top, so there is some heat that is constantly warming that air. But they have a refrigeration system that's constantly keeping that box cool, so it doesn't flow out like it does on a front door. So that's a pro and con from one to the other. But we have other cons to upright freezers with shelf evaporators. Those and the chest freezers don't defrost. So
Yes.
yeah, go ahead, Ricky.
That's what I was going to ask about that freezer because I didn't see a defrost. I didn't see a defrost heater anywhere in there. So when you said the temperature turns off, well, you said the compressor turns off at a certain temperature. Is it just manually defrosting
Well,
that happens?
let me answer that question in 1 minute, and
Okay.
because I did anticipate that the next slide or so is going to get right into the answer of your question, and then if so, I will clarify it. So it'll shut off like at 32. In this case, it's a freezer, so it's going to shut off at like -5, -10 degrees, and cycle back on maybe about 10 degrees above zero, and keep an average of 0 degrees in the freezer. But we don't have a defrost system, and in a freezer, you couldn't have any type of defrost system in there except for adding a heating element like most refrigerators have an actual electric defrost system in there. But when they created the first refrigerator, they created a cycle defrost. Now, if you look, we have an evaporator heater down here, which would be the same as a defrost heater, and we even have a heater in the drain when we defrost. Okay, so two things happen here. When this thermostat closes, and I'll do it in a different color, let's say green, power goes in when the thermostat closes, goes through this thermostat, and the compressor is running and cooling. But the heater is not energized right now because the thermostat has no resistance here, so the electricity is just going to bypass that heater. I don't get too much into basic electricity, but that's what happens. When the thermostat's on, the compressor's running, and it's cooling. Now when the refrigerator reaches temperature, that thermostat will open like you see here, and power will run through the two heaters and through the relay and the compressor. So now the compressor is not going to run because the heaters are going to take so much electricity, the compressor doesn't have enough electricity to run. So we call this cycle defrost. This was one of the first defrost systems that were added to help get the ice off that tubing. Now, when we cool, we want no more than about 1/8 to 1/4 inch thickness of ice on an evaporator. You got more than that, you're definitely having a defrost problem. But in cycle defrost, two things happen. Thermostat opens, turns on the evaporator heater, turns on the drain pan heater that is below the evaporator so it doesn't freeze it up. But what happens to the system pressures when the compressor shuts off?
What's up, the rise?
Well, one rises, the other one falls, right?
Okay.
So your condenser is high pressure, so it's going to go down. Your evaporator is low pressure, so it's going to go up. We call it what when the compressor's off? It equalizes.
Equalizes, yeah.
Yes. So when the pressure goes up on the evaporator, so does the temperature of the evaporator. So internally, the Freon is helping you with that defrost system. So we have this thermostat that's going to cycle, but that means this refrigerator will defrost every time we shut the compressor off. So what are we doing? We're adding heat, right? So now we add heat, the thermostat's going to say, hey, it's hot, and turn the compressor back on. So you have no point that this refrigerator is not using electricity either for the compressor or the heater. It's either defrosting or cooling, defrosting or cooling. It did keep a temperature and it did work, but notice that we have no defrost thermostat. We don't have a thermostat that shuts the heater off, where let's say the operating thermostat shuts the compressor off and we go into defrost. It'd be nice to have an evaporator defrost thermostat there that would shut the heater off, and then the main thermostat could still be off where everything's off, and then the main thermostat closes and we go back into cooling. That would reduce the amount of electricity we use, but in this case, it's going to cool, defrost, cool, defrost, cool, defrost, and that's called cycle defrost. Now, I just want to reemphasize what I was talking about with the, this being a basic class and working its way up into more complicated things. I want to go through all these components and do more as far as explaining each one of the components and what they do. But, in my email, if you read what I wrote, is, guys go to customers' houses and they can see a broken ice maker and it's not making ice, and they throw an ice maker in, they're done. They don't really understand the theory of how the ice maker works and what's causing it to cycle and why it's not working. They just know it's not working and they replace it. And, I have a lot of people that come up to me and said, wow, man, I really want you to train me. You know your stuff, this and that. And it's like, yeah, I can train you, but, I've been doing this for 40 years. And I took a basic school like what I teach. And I learned a lot of theory. And you're like, people don't want to sit there and read and do all that theory. They just want to take it apart, put it back together, and test things. And they don't really understand the parts they're testing, and this is what this is all about. That you become a true technician when you understand everything. And it doesn't mean you understand everything the appliance has to give. Something new comes out, and I have to learn it. When I first started, we didn't have computer boards, we didn't have dual evap systems, and we didn't have R600. So just like you guys had you learned, a lot later than I did, so you didn't see all these old systems like I saw. But that's what I started with, and I grew up with them. So anyways, going back to the class here. So we have pros and cons to the system. It uses a lot of electricity. It's not that efficient. We're adding heat, removing heat, we're adding heat, removing heat. And because we don't have no fans or anything like that, the air circulation throughout the box requires natural air circulation where hot air rises and cold air falls. So we create a natural convection of airflow that it creates air circulation all on its own. When the evaporator gets really, really cold, that cold air falls from the bottom of the evaporator, but the hot air is rising to the top. So it creates a natural convection that way. That's why in your homes, most of your ACs, the vents are in the ceiling. But if you go up north, where do they put the heater registers or the vents? Usually where? I couldn't hear you, Douglas. You're muted.
On the floor.
On the floor. Well, why do they put the heater vents on the floor up north? Because hot air rises. So if they pump it from the top, it's going to go right out the top vent and go right to the ceiling. By pumping it on the bottom, that hot air rises and then starts creating your natural convection of airflow in your room, which eventually heats up the entire room. So that's why you have heat registers on the floor and you have AC vents in the ceiling. So we introduced defrost, but how can we improve on cooling and efficiency? So government, even back then, they weren't as much as they are now about making it less energy consumption in these products. So we had to change the way our system is. Now hold on one second. I want to bring something up here. Which book is it? One second. Here it is right here. So if you look here, we've added some stuff. Let's go to this one first, this image here. So we added some more components. So what was added to that last circuit?
Looks like a condenser fan. What else? Evaporator fan.
Yeah, you got that. Yeah.
So if I go back here to this image right here, let me clear off this drawing. Copy. And let's go here and I'll just paste it right here. Paste. So you can compare the two. So if you look here, this is the same system, but we added 2 fans. Some units have a static condenser in the back, they have no condenser fan, and the evaporator fan really made it important because what we were talking about, the first couple of units were just freezers and not refrigerators. And if we go back to the very first slide here, I want to look at this box that this guy's looking at. So that compartment he's looking at is where they put that block of ice. All right. Notice the opening here. Why are we putting this wall here? Because if it's a cooler, I don't want this wall here because this is just shelves over here and there's just a storage compartment down here. So if I put that ice block here, if I got a wall here, wouldn't it be better if the wall wasn't there so that the food's closer to the ice?
Well, maybe you don't want food to freeze. I'm guessing.
Well, it really wouldn't freeze. I mean, I'm sure, Ricky, you've used a cooler and packed it filled with drinks or beer or whatever, and you could pack it completely with ice and put the drinks in it. They don't freeze. They get cold quick because that ice is absorbing the heat, but it doesn't freeze. So why did they put this wall in here? Just for the understanding of how a refrigerator works. What does the fan do?
Circulates air throughout both cabins.
It's
freezer and the refrigerator.
Circulates the air. So if I put a block of ice in here, the cold air is going to fall. This isn't a solid shelf. This is like wires here where air can go through. So the cold air from the ice is going to drop to the bottom of the box and migrate over here. But what's going to happen here? The hot air is going to come out, and we're going to create a natural airflow with that block of ice. So we're going to cool the whole box. I don't know how long that ice would last because it would last, I guess, probably about 3 to 4 days because it's solid. And the only reason why I said that is I've been working on a lot of commercial ice machines in my class, and I filled up the bin underneath, which is not refrigerated. It's just like a cooler. And I turned the ice machine off on a Friday or Thursday, which was the last day of class, and came back on Monday, and the bin was still half filled with ice. But there was no new ice being made, and it wasn't refrigerated. So it stored ice for 3 or 4 days. And I'm sure if you had something like those Yeti coolers, you could pack ice in there and probably keep ice up to a week or 2 inside those coolers, depending on how well they're insulated. So the drawback is you can see how well insulated this door would be, but every time someone opens and closes that door, all the cold air it had rushed out and warm air rushes in. So that would affect how efficient it is. So the fans help circulate the air. And let me get back to that diagram now. The fans help circulate the air. Oh no, sorry. The fans help circulate the air. One is to cool the condenser, and one is to cool to cool the box. Now we're talking refrigeration. There's no such thing as cooling. It's all heat absorption and releasing that heat somewhere else. So we can run an evaporator fan and circulate the air over the evaporator. But doing so also helped us develop the modern refrigerator, which had a freezer next to it, because the original refrigerators were just coolers and they didn't really have a separate freezer. They started doing the little refrigerators that were like office size. Give me 1 second here. Just give me 1 second. So they had refrigerators like this one here. If you look at these units here, and these units had a little evaporator plate in them when they created the refrigeration system. Biggest problem with these is they don't have defrost, and a customer doesn't know that's a refrigerant system, so they'll take an ice pick or a steak knife, and they'll let that ice get 2 inches thick before they start to try to remove it, and they pick at the ice to break it, and that evaporator is aluminum, and they'll stab right through it, and they'll destroy the evaporator, and it's really not worth fixing. There's been times where I fixed a few where you sand all the paint off and get all the oil off, and you use that two-part epoxy, you know, the two, like, looks like silly putty, and you mix the black and the white and it becomes gray, and I have successfully caused it not to leak, but I don't know in the future if it ever lasted. But these units had no defrost, they had no fan circulated, so the hot air would rise and come here, but then you could also keep a little bit of ice cream or ice trays in here. So before we put fans, this is like the biggest you could make a freezer inside of these refrigerators. Even full-size refrigerators, you can see here that this was the freezer compartment here and the rest was the refrigerator. So going back to the presentation, the evaporator fan created air circulation, and through that we designed a separate refrigerator and freezer. And in doing so, I don't want to get too deep into this lesson today. I want to go in tomorrow to talk about, not tomorrow, but the next class, talk about the internal components of a refrigerator and talk about damper systems, and I'll get into more electrical control systems, and I'll also talk about these components and how to test them and their purpose. How do they work, and what is the purpose of that part? Did you guys have any questions about any of the stuff that I covered for today?
No, I'm good.
Okay, I'm gonna send out some books and stuff like that with the next class video, and I'm gonna actually have some homework and stuff for people to do. I will post this in the members video section and eventually add it to the written material I have that's going to be individual chapters. But I don't want to, it seems like I sort of stopped abruptly, and the next stuff that I want to talk about, I want to be more detailed into it. I want to actually have refrigerators that I can show you and show how they work and what they do, instead of just show you pictures. So between now and the next class, I'm going to actually make some videos, small snippet videos, like I showed videos today. So when I talk about stuff, I can show a little video about, okay, you see this is how this works and everything. But I appreciate you guys coming, and we will resume again in 2 weeks, and I'll put an email out. But you guys have a great day.